One thing, whenever you have like a probability type of problem, is you have to sort of consider or ask yourself, well, first off, are these, if you have multiple events, like picking a card, are these independent or dependent? Because that sort of determines how you set things up. So independent events, you're allowed to multiply probabilities. So I just want to write this down. And dependent events you can't, because in a dependent event, basically you picking a card then affects the probabilities of the other cards. You know, if you take one card from a deck of 52, now there's 51 cards to choose from, so the probability of your next card is different. So if you have independent events, it's really easy. You just find the probability of each event and then you just multiply them. So like the probability of picking, say, a red card, if they were two different decks of cards, you know, if you're like pulling from one set of decks and then another set, those could potentially be independent because the decks are separate. In our card situation, they're not independent, they are dependent, because once you pick a card, your probabilities of all the other cards change. So we can't multiply probabilities. So then we have to go back to the counting problem idea, because we can't just find the probability of, or even the proportion of how many twos are in a deck or how many wilds are in a deck. We can't rely on those proportions to get the probability. So we have to do it, go to a counting problem. And that was where you're looking at like categories, and it's similar to permutations, where it's similar to permutations and combinations. So with permutations, you're like looking at, okay, how many probabilities do I have for this? And it's in a specific order. So the order matters. While combinations, the order does not matter. So then once you decide whether something's independent or dependent, if it's independent, you can just go straight to maybe how many events you have out of total and multiply those. It's much simpler than when it's a dependent event. And then you have to determine, does order matter, does order not matter? Now in our card example, order does not matter. It doesn't say that you have to pick two wilds first and then you pick your next cards are red. The order there doesn't matter, so then we're looking at combinations. And so we're still going off of the counting problem format where you multiply how many possibilities you have. So the counting problem format is like how many choices do you have the first set, then the second set, and the third set, and you multiply those together. So if I was looking at, let's say we had just a regular deck of cards with 52 cards, and I want to know, okay, if I pick, let's say I'm picking a hand of 5, so 5-card hand, and I want to find what the probability is of getting, let's say, 2 red cards, and then say the other 3 are black. The order that I have those doesn't really matter, so it's a combination. And I can't just say there are 26 red cards, 2 out of 26, or I can't say there's necessarily, out of the black cards, 3 out of 26, because once you take a card, that probability changes, because then the total number of cards that you have changes. So when we set up a counting problem with something like this, you're doing something similar where you need to find the total possibilities. And so you go back to okay, so we determined that, okay, this is going to be a combination. We go back to that counting problem setup where you multiply. And then we can think of this as multiplying our totals for the number of red and the number of the black. but we're doing combinations now. We're not just saying, okay, there are 2 reds and then 3 black, and that gives me 6, 2 times 3. We're looking at the total number of ways you can choose red cards out of, out of 26 possible red. There are, if we think of each red card, it's a different number, different suit. It's very distinct. So it's not just a matter of, okay, 2 out of 26 or whatever. There's more combinations because they're technically different types of cards. So this is where we go into the combination fact instead of just saying 2 or 26, just saying there are 26 choices for red. So we would be doing, there are 26 red cards and we're choosing 2 of them. But there's multiple ways to get those number of red cards. There's not just 26 different red cards. You're picking 2 and then you can do them in different orders. So we have to have a combination there. And then it's the same thing with the black card, where there's 26 black cards and we want 3 of them. So that card problem is using the same setup as the counting problem, but the counting is a little more complicated, and that's where the combinations come in. Because they're distinct. Each red card is distinct, or each black card is distinct because there's different suits and there's different numbers. So the whole process of a probability problem is first determining, are they independent or dependent? If they're dependent, then we go to our counting problem, and then we have to figure out, are these distinct choices or are they not distinct? If they were not distinct, if every red card was identical, then we could just literally do 26 times 26. If every red card was identical, every black card was identical. But they're not in a deck of cards, so we have to go back to our combinations. How many different ways can I pick 2 red cards out of 26 different red cards? And then that is how many choices or how many possibilities we have for choosing 2 red. And so then that goes back to the counting problem. And then the same thing with the black. So you have to then consider distinctness. To determine whether you just flat out take the number or whether you do a combination or a permutation. And if you have to do a permutation, if the order matters, like they say you pick your first red cards, you do the red card first, then we'd have to use a permutation here. But it doesn't state that. It just says, you're just having a hand of 2 red or 3 black, total for 5 card hand. And so the order doesn't matter, so we're doing combinations. So that would tell you the total number of possibilities for that, for a hand of 2 red and 2 black. Two red, 3 black. And then that is the number of events that you would use on the top of your fraction for the probability. Is once you determine those numbers, that tells you how many different ways you can get a hand that way. And then you would need to find, well, how many different hands are there? And that would be there. If you have 52 cards and you're choosing 5, that would be the total number of total possible hands you can have, with no restrictions, basically, on what is in that hand. So then once you've determined that, so we had to determine, okay, we can't use the independent, we can't just multiply probabilities, so we need to do some sort of combination, and we're setting it up like a counting problem where you multiply, then you set up the probability. So the probability of 2 red and 3 black would be then creating your probability where you have the total possible over, or the total of that specific event over the total possible hands. And basically, you can put this on in a calculator to determine those numbers. But basically, this is the once you do several probability problems, you see that there are like different setups. So this is like your first setup is if they're independent and you're just multiplying your probabilities. Second setup is if they're not independent, but you can figure out the possible hands, and you're just basically finding how many on top, how many are on bottom, and you just flat out divide them. Basically, the total number of choices out of something, and that's usually if you're picking like one category of something. This is the third type, where you're picking multiple categories and they're not independent, so you have to use your counting problem setup where you're multiplying, and then that is on the top of the fraction, and then you have the bottom as the total. So this is a third common setup that you see, and that card problem demonstrates this setup, and this is another way that you can do it with just a deck of cards. This would be the sort of thing that you do if you're like playing poker and you're trying to figure out what is the probability of getting a certain hand, is you would sort of set it up this way, where you would have to use combinations because the order of picking the cards doesn't matter, and then you would be dividing. But this is like the third kind of setup. So it's a matter of just identifying your situations to identify which of the three setups that you have. And then once you've determined that, then you kind of know, okay, this is how I set up the problem. Does that help?
Yes, ma'am.
Okay. So I could even go and, where is my calculator? Figure out this particular one. It's definitely combination problems. Anything with combination or permutation, I just generally will use my calculator to figure out the value, because otherwise, you could do it by hand, but it's time consuming. So let's see for here. So we have 325 there, 2,600. 2598,960. So if I just multiply on the top, 845,000. We've got almost 2 million possibilities, over 2 million. And this comes out to 0.325, or it's about 32.5% of getting a hand of 2 red and 3 black, which makes sense because you basically have half of your deck is red, half of it is black. So the probability of getting a hand, if you're just looking at those colors, should be relatively high, because we don't care about whether they're specific suits or numbers. We're just looking at flat out the color. So Chancey, I see you just joined. I just went into an explanation, a further explanation of the card problem with just a regular deck of cards, but also explaining, taking a look at whether it's independent or dependent to determine the setup, and whether order matters, which determines whether you're doing a combination or a permutation, whether your options are distinct or not distinct, because all of those kind of help you decide what kind of setup that you would need for a particular problem. Do you have anything particular that you want to see me work out, or have questions on anything? No, just listening in. Okay. Timothy, did you have anything else?
No, not really. Just, cover whatever you'd like, and I'll
Okay.
continue learning.
I'm gonna open up the textbook and see if there are any good examples that I can pull. It's gonna take me a little bit to open it up. Complementary probability. I can definitely find an example of that. In question 5. Question 5 is another one that people struggle with. The thing about question 5 is that each fire truck basically has their own possibility. The probability of one truck being available does not affect the probability of other trucks. So those are independent events. And when you set up your probabilities, you're still basically using a counting problem, but you get to multiply the probabilities. And so you think of it as you're multiplying the probability of each truck. Let's see, I'm trying to find. Here's a good one that's sort of similar. I'm just going to paste this. So in 9.7, this is problem number 47. It says a shipment of microwave ovens contains 3 defective units. A vending company purchases 4 units at random, and then it's got basically 3 choices for the probabilities, which are very similar to the kinds of things on the fire truck problem. So a shipment, oh, it didn't copy the number. For whatever reason, the number didn't copy. It says 12 in the textbook. So a shipment of 12 microwave ovens. So the probability here of one of them being defective is 3 over 12, because in that single shipment, 3 were defective out of 12. So I can reduce that. That's a quarter of the shipment was defective, which is not great. That's a pretty bad rate. And so we've got a vending company that's purchasing 4 units in random. So this is similar to, we've got 2 trucks, and instead of defective, we're just basically, is it in working shape or not working? Is it available or not available? So the probability that all 4 units are good. There's 2 different ways that we can think of this. Now, this is independent because the probability of 1 unit being defective does not affect the probability of another unit. They're not related, which means that we can multiply our probabilities together. So we're going to have 4 probabilities we're multiplying. So there's different ways to think about this, but if it's defective 1/4 of the time, that means 3/4 of the time it is good. So the probability of 1 unit being good is 3 over 4. And then if you want 4 of them, you just simply multiply all of those probabilities together. So it's actually 3/4 to the 4th power because there are 4 units. And the probability of 1 does not affect the probability of the other. So this comes out to 0.316, which is 31.6% of the time. Or basically, there's a probability, 31.6 probability you're going to get 4 good units, which not great. Not great, but that's because there's a high probability of them being defective. So then 2, it says exactly 2 units are good. So 2 units are good means the other 2 have to be bad. Exactly 2. So that would be 2 good, and then the other 2 are bad. So they have the 1/4 probability. So we've got 3/4 times 3/4 times 1/4 times 1/4. So this comes out to 0.035 or 3.5%. Now our last one here, at least 2 units are good. So the at least is where usually people start getting confused, because that at least 2 means you have a probability that are exactly 2, or you have the probability of exactly 3, or the probability of all 4. So you're adding essentially probabilities here. Oops. Because at least has multiple possibilities. Exactly 2, exactly 3, and then exactly 4. Sometimes we can use the complement. This would be the same thing, and the complement is how I got the 3/4, but that'd be 1 minus the probability of none being defective, or the probability that 1 is defective. So you could think of it the other way by finding out the probability that none of them are defective, or the probability that one of them is defective or good in this case. Because it's binary choice, one or the other, if we have at least 2 units are good, this would be the probability that none are good or one is good. I'm kind of using the defective and the good interchangeably, but it depends on, are they asking if it's good or if it's defective, but the setup would be exactly the same. So we already found the probability of all 4 and the probability of exactly 2. So for a situation like this, I would probably not use the complement. I would just have to figure out, okay, what is the probability that exactly 3 are defective, and then add all of those up. And it should be under 100%, because probabilities can't be over 100%. So we would need to figure out the probability of exactly 3. Let's see. And we're looking at our goods. So 3/4 and then 1/4 would be bad. Oh, I missed a decimal point. I multiplied it and I didn't get. I got a number that was way too big. Okay. That's 0.105 or 10.5%. So if you want the probability that at least 2 of them are good, you would add exactly 2, 3.5%, plus exactly 3, and all 4. And that comes out to 45.6. But it's very similar. I've done this one very similar to problem 5, where you're going to have to be multiplying your probabilities together because they're independent events. And it has the same same wording here, exactly 2, or at least, although they don't have exactly 2, it'll be like at least 1 is available, that sort of thing. Does that help? Okay. Good. Oops. I'm opening up somewhere in here the solution manual. See if your brain hurts a little. Yeah. As I have in my announcement, probabilities are not easy for people, and our brain doesn't. It like the way that our brain thinks about probability, it's not natural. Like the way that it makes sense to us doesn't always match how you actually do probabilities. So it is very hard. And so I'm looking at the textbook here. So what I did here is the way that I did this, because I wanted to do this very similar to the fire truck where they're independent. So I made the assumption that these were independent. Which in this case would have to mean that they are separate shipments. Because if it's in one single shipment, then they're not really independent anymore. I assumed independent so that it was similar to number 5, where one doesn't affect the other. And the wording doesn't necessarily make it clear whether you are to assume independence or not. It just says they purchases 4 units at random. It doesn't make it clear whether they're, making a single purchase, they're coming in the same shipment, or whether they were separate. Let's say these were not independent events. So, which they were coming in the same shipment. And this is back to the wording. It's the thing with these probability questions, it's very difficult to determine what they mean. And so I am not a fan of probability for that reason, just because it isn't clear. Because I would like, it's like, well, which formula do I use? You have to kind of make assumptions based off of the problem. So if we assume they are dependent events, so let's go back to all 4 are good. So you're got 4. And in this case, because they're not, they're dependent, we can't rely on this proportion of 1/4 of 25%, basically. We can't use that anymore because to dependent events, you can't multiply probabilities. So we have to go back to our combinations and our permutations and counting problems. So I'm assuming that the order here doesn't matter for the order that you pick the ovens or whatever. So we're going to use combinations here. So if we've got 3 defective, that means we have 9 good. So if we have dependent events where 4 are good, then we have 9 good ones to use, and we're choosing 4 of them. And we have 1 spot because we're assuming that all of them are going to be good. And then, well, there's 12 units total, and you're choosing 4, so that would be your probability. So this is similar to the card problem if you're assuming they're dependent events. So all 4 are good. We basically have, if you're looking at a good problem, and we have good times bad, but we don't have any bad ones. So we just literally are, okay, if I pick 4 out of those 9, how many ways can I do that? And so let's actually show how this can change the numbers, basically. So that's 126 possibilities. And 495. When it comes to 0.255 or 25.5%. So if they're dependent events, if they're coming in the same shipment, you have a 25.5% that your 4 are good. So you can compare that to when they were independent, that was about 31.6%, but they're sort of comparable here. So now let's look at exactly 2 units are good. So again, this is going to be similar to the card problem because these are dependent events. And so you're looking at good, and then you are going to have some bad ones in there because you're going to have 4 units total. So we're going to have to multiply our combinations just like with the card problem, where you have, okay, we're choosing 2 from the good pile, and then there are 3 bad, and we're choosing 2 from the bad. And so it's a counting problem where you're multiplying your choices here. So to get our probability, it would be 9, choose 2, 3, choose 2, and then we still have our total of 12, choose 4 at the bottom. So you're looking at, okay, how many ways do I have to get good ones? How many ways do I have to get the bad ones? And then you're multiplying those together. So 9 choose 2 is 36. 3 choose 2 is 3. And then we know 12 choose 4 is 495. That is 108 over 495. And that is 0.218 or 21.8%. So you have a 21.8% chance of getting 2, exactly 2, only 2 good ones. And that's a very different probability from when we're assuming they're independent events. So independent versus dependent really matters here on how you do the problem and what your overall probabilities are. You have a higher probability of getting 2 good if they're coming in the same shipment. Now, the last one was at least 2 units are good. Oops. This was set up the same way that we did it before, where you can either do 1 minus your probability that none of them are good, or one of them is good, or you can add your probabilities. So we can do it. The easier thing to do right now is to add the probabilities like we did here, but we need to find, well, what is the probability that exactly 3 of them are good? So the probability that exactly 3 are good. So there's 9 good ones. Now we're choosing 3. And then out of the bad, we're just choosing 1 instead of 2. So that we have 4 total. And then we have our 12. Choose 4. Interestingly enough, that is also 3 choices there. 84 times 3, or 495. 252. 495. And that's 0.509, or 50.9%. So that means the probability of at least 2 would be the probability of exactly 2, which is 21.8%, plus the probability of exactly 3, 50.9%, plus the probability of exactly 4, 25.5%. So you add all those together, that comes out to 98.2%. So if you look at it that way, that you ordered 4 units from this single shipment, what's the probability that at least 2 of them are good? That's a really good probability that you're going to have at least 2 good units there. But it's very different from when we treated them as independent events, where it came out to 45.6%. So independent events and dependent events, how you do the problems are very different. But as I said at the beginning, and this is before you came on, Chancey, there's basically 3 different ways to do a problem. The first way is that you are simply just finding a probability like this. So like 1 over 4, just how many you have out of the total. Second way is independent events, like we did here, where you multiply your probabilities. And then the third is dependent, where you start having to do these combination things, where you multiply your combinations over the total. And it really matters, basically, if it's independent or dependent. And it's really rough if the wording of the problem isn't really clear about that. Like in this case, it doesn't make it clear. You have to make an assumption. Are we going to assume that they're from the same shipment, or are we assuming that they're not from the same shipment? So it is very difficult for probabilities, especially when you're trying to read these word problems. Has that added to your understanding, or has that confused things? Okay, and if I wanted to use the complement here, if we said, okay, oops, what is the probability that at most 1 good unit, so at most 1 good unit would be the probability none are good, or the probability that 1 is good, and that is 1 minus the probability of at least 2. So this would be where you could use the complement, because at least and at most are sort of complements of each other, as long as you have that cutoff part just right. So that would be 1 minus, and we'd use the decimal point version, 1 minus 0.982, 0.018, or 1.8%. So the complement is useful if you're given like the probability of something being good and you need the probability of it being bad, or sometimes depending on what you've already calculated, sometimes it's easier to use the complement because it might be quicker if you already have, if you have one of those things already calculated. So that's where the complement comes into play. It's just kind of thinking about, you have to kind of look at the words and being like, okay, if these are good, then the opposite of that would be 1 minus. Yeah, complement is really good if you have two choices because it's pretty easy. If you start having a lot of choices, like here, it's just a probability. Like let's see if I go back here where I wrote it. If we were just doing the probability of none and 1, that's not too bad. Yeah, the two choices add up to 100. So the thing about a complement is that those probabilities always have to add up to 100. So because it's 1 minus. So so if you do something and your complement doesn't add up to 100, or there's, your groups don't add up together to 100, that would give you an error. Like, let's say instead of here, we did the probability of at least 2. What if we had included 2 in our probability or forgot to include it? You would have ended up with your complements not adding together to 100. And that would give you an indication that you're missing something, basically. So if you try to use a complement and it doesn't add up right with what you were using before, what you think it should be, then you've got an error there. So hopefully that helps. I would definitely use the complement on the homework because the one question that's asking for it, you already have the other thing calculated. So it's just really easy that you just take 1 minus that and you get the answer. But you can also do it the way that we've done it here and just maybe more work. And another thing that comes up is mutually exclusive events. That does not apply on any of the things that we've done so far where it could be counted as both. Because, well, in this situation, you can't have an oven that's good and bad. So, they're mutually exclusive, so we're allowed to add those up. But if they weren't, if there was some overlap, then you would have to subtract out. But independent events are basically also mutually exclusive. Not always, but they generally are. So you can just simply add those probabilities like we did here. One, like a red card and a queen, those would be ones where they're not mutually exclusive because you can have a queen that is also a red card. So that's where you then have to think about, that's where they're not mutually exclusive because there's overlap. If you're counting the number of red cards and the number of queens, a red queen is also in that bucket. Actually, let me just drop down the textbook here because they actually have a picture here with hearts and face cards. So like these are some overlap here because you have some where they are both hearts and also part of the face cards. So in this situation, you're drawing one card at random. So one card at random means that we do not need to use the complement formula that we were using, combination formula, because we're just choosing one card. So we don't have to worry about multiplying different types of cards. It's just one pick that we're choosing So we're not, if we're picking like 2 cards at random, then we would have to get a little more complicated. But with 1 card at random, we're looking for a heart or a face card. And this is where you would have to subtract out the probability of a card being a heart and a face card because you count it twice. You would be counting it with the heart and you'd be counting it with the face card. So they found hearts 13 out of 52, face cards are 12 out of 52, and then there's 3 that are overlapping. So 3 out of those 52 cards are overlapping. And so your probabilities, you'd have to then subtract out that overlap. This type of situation usually occurs if they're asking you to do this or this. So if you were asked only to find the probability of getting a heart, you wouldn't have to worry about it. If it says a heart or a face card, then you would do something like this. Now, if it said a heart and a face card, that gets a little more complicated. That can start going, well, again, you're going to be picking 2 cards then if you want a heart and a face card. So then you have to go into the combinations that we did. And let's see, there still would be some overlap there because you would have a card that would fall under the heart or the face card. So you would still have to do a subtraction deal going on for if you're looking for a heart and a face card because there is some overlap between there. But I don't think there's any questions like that because that does get a little bit more complicated. So yeah, that's mutually exclusive, or things that are not mutually exclusive where there's some overlap. And that's just, do they have anything in common? And I think pretty much everything is mutually exclusive on the homework. There's not anything where you have to worry about overlap. But probability is very difficult. So if you're still not 100% on it, don't feel bad because I've been teaching these probability stuff for several years, teaching pre-calc, and it's still like, oof, still kind of like, I take it slower because I'm like, am I doing this right? It's just something that's very difficult for humans. Yeah, I could have blackjack either. I mean, those people that count cards, like, they have to really memorize all these probabilities. I do not gamble or do any of those things. Just, well, it's a lot of work to go through all these probabilities, but also mathematically you're more likely to lose. So it's like, well, I'm not even going to bother.